Swayam Prabha. Digital India. Educated India.
Welcome to this another session in our discussion on aerodynamics. In the previous class, we have talked about the idea of similarity parameters, and we have talked about dynamic similarity. We saw that starting with the governing equations of continuity, momentum, and energy, we can non-dimensionalize these equations and obtain these non-dimensional groups, which we saw, where the Mach number, the Reynolds number, the Prandtl number, the ratio of CPCV, and also we saw that in some cases the ratio of T infinity by TW can come out as some of these similarity parameters. We made the observation that if you have the flow problem on two geometrically similar bodies, of course, of different scales, so they are in the same shape but of different sizes, and somehow if these non-dimensional parameters that we are referring to as similarity parameters, the Mach number, Reynolds number, etc., if they are same between these problems, so Mach number is a ratio of V infinity by A infinity. In these two problems, maybe A infinity and V infinity individually are not the same with each other. So V infinity for the small cross-section wing and V infinity for the large wing may be different. A infinity for the small wing problem and A infinity for the large wing problem may be different. But as long as that V infinity by infinity for the small cross-section wing problem matches with that of the large cross-section wing problem, and of course, Reynolds number, Prandtl number, all these things also match, we said that the non-dimensionalized plots of the physical variables versus the spatial extents, etc., will be similar to each other. And part of this is quite easy to understand. If the non-dimensional forms of the governing equations are the same, if the coefficients of these equations are the same, because your non-dimensional parameters occur as coefficients of the governing equations terms. So if the coefficients are the same, the governing equations are the same, and the non-dimensionalized variables, the boundary condition in terms of the non-dimensionalized variables are the same, then of course the results in terms of the non-dimensionalized variables will be the same across different problems, because we are pretty much solving the same problem. Once you get the non-dimensionalized version of the solutions, then for particular problems of the particular scale, you can get the dimensional version of the parameters, okay, by multiplying it by appropriate reference values. Now, while we were talking about that process of non-dimensionalization and then obtaining the non-dimensional groups, we said that we would spend some time in looking at how these governing equations themselves come into existence. Okay, this is an introductory course, so I think it makes sense to at least have a feel for. So in the previous class, we saw that given the governing equations, how do we obtain the similarity parameters? What is or how does the idea of dynamic similarity come from? But at that point, we did not spend time looking at the derivation of these governing equations. So in this lecture and maybe in the next lecture as well, we will look at how these governing equations are obtained. So let me switch on my desktop recording. And as you can see, we have talked about these things briefly in the previous lectures as well, that the governing equations essentially stem from the conservation of mass, the force momentum balance, and the conservation of energy. And depending on how you apply, or rather how you approach the derivation, you can get different forms of the governing equation. Okay, for example, if you start with an infinitesimal volume of fluid or infinitesimal region in space through which a fluid is moving through or moving across, you end up getting the differential forms of the governing equations. On the other hand, if you consider a finite volume of fluid a fixed mass identity moving through a flow field, or if you think of a finite volume in space through which a flow is moving across, you will end up with the integral forms of the governing equations. As I said in the previous lecture, the integral forms of the governing equations will have a preponderance of this integral sign, surface integral, volume integral, etc. Of course, derivatives can occur inside these integral signs, but nonetheless, you will have these dominated by these surface integrals and these volume integrals. On the other hand, when we are looking at the differential forms of the governing equations, we will have the preponderance of the dou by dou t and the dou by dou xyz, depending on which Cartesian coordinate system you are involving in the problem. In some cases, if you are looking at a 2D problem, then you will see that the derivative is in one particular spatial direction can be neglected because it's a 2D problem. But in 3D problem, of course, you will have d by dt, d by dx, d by dy, d by dou z, and all those things. Also, depending on here, we are deriving or we are going to derive the governing equations in the Cartesian coordinate system, but you can also derive it for the cylindrical coordinate system, for the spherical coordinate system, etc. So what will happen is your governing equations for mass, momentum, and energy conservations will look a little different from each other depending on which particular approach you are taking, whether you are starting with a infinitesimal volume or a finite volume, whether you are showing you are explicitly uh, deriving it for the Cartesian coordinate system or for the differential form. For the differential form, if you are using the Cartesian system or the polar or the cylindrical, if you are explicitly showing the the form of these relationships for that choice of coordinate system, then these equations can look a little different from each other, but they talk about the same principle. Either they talk about the conservation of mass, or they talk about the force momentum balance, or they talk about the energy balance. Okay, the forms might be different, and it can actually be shown that these forms are interchangeable. Okay, so if you have, say, the continuity equation in the integral form, through a systematic approach, you can actually obtain the continuity equation in the differential form from the integral form of the continuity equation, which in some way indicates that the correctness of these things, because since the physical principle is the same, depending on which particular approach you take should not change the result of this conservation statement. So here we will quickly see the derivation of the continuity equation that is based on mass conservation, and we will look at these two approaches. Okay, so this is, remember we said that you can start with an infinitesimal volume. So this is my dx, this is my dz, and this is my dy. So here we are talking about an infinitesimal volume. Now it is important to note that sometimes we will talk about an infinitesimal volume in space through which a flow is moving across. So this is something of the sort of the Eulerian approach. That is, we are fixing our volume of interest, the dx, dy, dz volume, and my flow is moving through, moving across the walls of this infinitesimal volume. In the case of the derivation of the continuity equation, we will use this infinitesimal volume through which a flow is moving through. On the other hand, we will see that when we derive the differential forms of the force momentum balance or the momentum equation, or the differential form of the energy equation, in those cases, we will consider a small element dx, dy, dz of the fluid that is moving through. Okay, so in that would be an Lagrangian approach where that infinitesimal element represents a fluid parcel of fixed mass identity. Okay, and we will see how assuming that leads us to the governing equation of momentum balance, or rather momentum force balance and energy balance. So in this case, the infinitesimal element is an infinitesimal region in space through which the flow is moving across. Okay, so it is not an infinitesimal element of or a infinitesimal parcel of fluid of fixed mass identity. Now you can actually do it that way as well. Okay, you can think of of a fluid parcel of fixed mass identity whose mass is not changing. As you move through the flow field, it is deforming its shape and size. They might be changing, but that is another approach. So in this particular approach of the differential form of the continuity equation, we are saying that let us look at this region in space bounded by dx dy dz through which flow is moving across. So now we are looking at, so this is the y and this is the x-axis. So we are looking, you can think of like we are looking along the z direction in this way. So we are looking at the fluid element in this direction. And so we see something like this. So this is of extent dx, this is of extent dy. And of course, in the direction of the z direction, so that's the, you can, so it's this is the vector that is coming out of this xy plane. So that is the z direction, and you think of that as an extent of dz, this one. Now what is happening here is, say the flow in this on this plane has a density rho and a u component of velocity u. So then the mass that is flowing in through this wall of that infinitesimal volume in space is given by rho u dy dz. dy is the extent of this wall and dz is the extent of the wall in the direction normal to this xy plane. So this is the amount of mass that is entering through this wall. Now the mass that is leaving this wall can be given by rho u, essentially a Taylor series approximation. So rho u plus the rate at which rho u is changing with respect to x multiplied by the extent through which we are moving from this wall to that wall. So then the mass of fluid leaving this wall is rho u plus the rate at which this rho u thing is changing with respect to x multiplied by the change in x. And then of course we have to multiply it by the area of the wall through which that flow is happening. So again, the area of this wall is same as the area of this wall given by the product of dy and dz. Similarly, the y component of velocity is v, density is rho. So the mass flow that is entering this wall is given by rho v dx dz. Dx dz again, this is dx, and then this in the direction normal to this plane xy, there is the extent dz of this surface. So the mass flow entering this infinitesimal volume is given by rho v dx dz. Similarly, similar to this one, the mass flow leaving the top surface would then be rho v plus the rate at which rho v is changing with respect to y, because we are moving along y. The rate at which rho v is changing with y multiplied by the extent through which we are moving in the y direction. Okay, so this gives the rate at which rho v is changing with y, because we are moving to go to this wall from this wall, we are moving in the y direction. So we need the rate at which rho v is changing with y, and then we multiply that rate by the real displacement in the y direction, which is dy. So then the mass coming out of this wall is given by rho v plus dou by dy of rho v times dy multiplied by dx dz, which is in the same idea as this one. Similarly, we will do the same thing in the z direction. Now what we will say is the time rate of change of rho times dx times dy times dz is nothing but the accumulation of so the increase of mass in this infinitesimal volume would be the accumulation of mass because of the imbalance between what is flowing in and what is flowing out. Okay, so what we do is, what is then the accumulation due to imbalance in the x direction? It is what is coming in minus what is going out, and that ends up giving us this term. Similarly, what is going in the y direction and what is coming out of the y direction would give you the difference, would give you the accumulation due to imbalance of this mass flow in the y direction. Similarly, in the z direction, you will get this. Now, this dx dy dz is fixed because we are looking at a fixed region in space. So we can cancel those, and then we are left with dou by dou t of rho is given by the divergence of rho times the velocity vector. In fact, this way we obtain the differential form of the continuity equation. On the other hand, if you see what we have on the right hand side here, here we are taking a finite volume of space through which, if you think of a small differential element on the surface of this finite volume, if this is the surface normal vector, so essentially the direction is normal to the surface, and the magnitude is equal to this small surface area that is bounded by this line. So the product of v vector times the ds vector multiplied by the density gives us the mass flux that is leaving this volume. Okay, so you see that when these v vector and ds vector are in the same direction, we are talking about a positive v dot ds value because v and the ds are in the same direction. On the other hand, flux or mass that is moving in, there your v vector and ds vector will be oppositely directed, or at least on the average they will be oppositely directed. So in that case, if you so the time derivative of the density times the dv integral over this volume will be seen in the similar spirit as this one, in the similar spirit in which we obtain this one. The time rate of change of mass, so this is the time rate of change of mass within this finite volume, will be given by the accumulation of mass due to the influx and the outflux of mass through the surface of this finite volume that we are looking at. Okay, so here our flow is moving through this finite volume in space. The change in mass within this finite volume, which is given by dou t of this integral, is nothing but the difference of what is coming in minus what is leaving. Okay, so when you do this, this is essentially, this is the accumulation term, because where the direction of v and ds are similar, the negative sign comes in. So then your accumulation becomes positive. So whatever is entering, because if you remember or if you observe this thing, that where the fluid is leaving the surface, this v dot ds term becomes positive. Whereas where the flow is entering, if you think of surface like this where the flow is entering, so ds is directed in that sense, but your v is directed in that direction where flow is entering. So if you think of this one, you see this one is somewhat similar to this portion. Okay, so here we are talking about an infinitesimal volume. Here we are talking about a like a mass within a finite volume, and this one essentially is influx minus outflux. So by putting this negative sign, your influxes become positive, because if you don't put the negative sign, then the v dot ds for the influx is negative. By putting this sign, the influxes become positive, the outfluxes become negative. So essentially it is still something of this sort. So then this one gives the accumulation of mass because of the flow of fluid across the surface of this finite control volume. And then, so this is the accumulation due to imbalance of what is coming in and what is going out. And this is the resulting change in mass within the controlled volume. And then overall, this gives us the integral form of the continuity equation. So essentially, it's a single step derivation. There is nothing more to say about this. So while for the infinitesimal volume based derivation of the continuity equation took us a few extra steps here, the integral form of the continuity equation comes almost in an intuitive sense. Okay, the only important thing to notice here is in the way we derived this, we looked at finite volumes, well, infinitesimal volume in space through which a flow is moving through, finite volume in space through which fluid is moving through. In fact, once we are done with the differential forms of the governing equations, we will look a little bit in detail about the integral forms, and we will talk about something known as the Reynolds transport theorem, which we will see will be a very important launchpad for a great number of concepts in fluids. Okay, Reynolds transport theorem, something related to the integral form of the conservation equations, Reynolds transport theorem. We will talk about things like control system, control volume, and how you can obtain the force on a control system by looking at the flux of momentum across the boundaries of a control volume, etc. So we will keep in mind that Reynolds transport theorem, when we are done with the differential derivation of the differential forms of the governing equations, essentially this is the differential form of the continuity equation, and then gradually we will get into the differential forms of the momentum equation, energy equation, etc. But here I wanted to emphasize that the differential form of the continuity equation, or rather the continuity equation, can be derived in these two ways. One will lead to the differential form, other will lead to the integral form. Before we get into the derivation of the momentum equation, I would want to show how remember I said that although these two forms, so this form, although this form looks a bit different from this form here, I said that these two forms are the same. So if you look at this particular slide here, it's kind of a little evident that, so this is our differential form of the continuity equation, mass conservation equation. This is the integral form of the continuity equation. Now there are two important vector identities, okay, so that will allow us to move from surface integral to a volume integral. Okay, so depending on whether this term, whether we're looking at a like a vector dot product. So you see here we have a vector dot ds. On the other hand, here we have a scalar times ds. Depending on whether which form we are looking at, we can use these identities. So in this case, you see that this is a surface integral and this is a vector and this is a vector. So essentially we are looking at a problem similar to this one. So here, so applying 3 to 2, so applying this particular form to this equation, we can convert this surface integral of rho v dot ds to a volume integral of the divergence of rho v vector over the dv. So then your this form, so we will replace the surface integral with the volume integral. So we will replace this particular surface integral by this. We will replace this by this to obtain this form of the integral form of the continuity equation. So you see, right now we have these two volume integrals. Now, under some assumptions, your this dou by dou t can come inside this volume integral sign. We will see that if your volume is fixed in space and it's the shape is not changing over time, so it's not moving, its shape is not changing, then you can bring this d by dt inside. In fact, that is essentially the statement of the Reynolds transport theorem. So once we bring it in, then we can just combine, because both of them are volume integrals. So we can combine them and say, okay, this is the volume integral of this term over the entire volume becoming 0. Now, for this thing to be satisfied, it is possible that this term is positive in some regions of this and negative in some other regions of V, eventually balancing out, becoming 0. But that is a very special case. But this is satisfied generically. So the only way in which this can be satisfied generically without any of those special considerations is when this thing actually becomes 0 at every point within this domain. So that then gives us that d rho dt plus this is equal to 0, which is nothing but similar to 1. So we can see here that starting with the integral form of the continuity equation. So this is the integral form. Well, rather, this equation 2 is the integral form of the continuity equation. By applying suitable vector transformations, we convert the surface integral to a volume integral first. Then we bring in the dou by dou t inside, and then we combine the terms in for these individual volume integrals into one term, and then we make the claim that for this thing to be 0, in a generic manner, where we in very particular arrangements it is possible that you can arrange it in some way to make it 0, but in a generic manner, and since this thing has to hold within any volume, so the only way in which it can hold is if that integrand is actually 0, and that you see that this is nothing but the differential form of the continuity equation. So starting with the integral form, we can arrive at the differential form. So once again, we see that the governing equations can be derived based on infinitesimal volume or finite volume. The infinitesimal volume will lead to the differential form of the governing equation. The finite volume approach will give us the integral form of the governing equation. But from what we just saw with respect to the particular case of the momentum equation, we see that the integral form of one conservation equation leads to the differential form as well. So we have to just make some appropriate mathematical transformations. So now we looked at the continuity equation. Now here we will be looking at the momentum equation, and as you can already guess that by we are looking at dx dy dz, then we are essentially looking at an infinitesimal approach. So this is an infinitesimal volume approach. Now in this case, you will see that we are using these total derivatives or the material derivatives, and if you might remember from this that we are essentially looking at some kind of a Lagrangian acceleration. That is, here my dx dy dz represents a chunk of fluid. Okay, in the continuity equation, dx dy dz represented a infinitesimal volume through which flow was moving through, the Eulerian approach. Here we are looking at a small parcel of fluid dx dy dz of fixed mass identity, and it is moving through the flow domain in that Lagrangian manner. So here when we say that, okay, for this parcel of fluid of dx dy dz, so in one case we are saying dx dy dz defines a differential volume in space through which a flow is moving through. Here we are saying dx dy dz define the dimensions of the parcel of fluid that is moving through the flow field. Slightly different descriptions. Okay, so for this parcel of fluid, the force acting in the positive x direction is given by pressure times the area of this face. Similar to the continuity equation, we have the z direction in this direction, so the dz extent comes into the picture. Okay, so this p times dy dz essentially is the force that is acting on this wall. Now, by now to find the force on this wall, all we have to do is p plus dou by dou x of p, so the rate at which p is changing in this direction, multiplied by the net amount of that shift in direction along that axis. So P plus dou P dou x into dx, and then multiplied by the area of this side. The area of this side is same as the area of this side, which is given by dy dz. Similarly, the force in the y direction is given by P times the area, and here it is P times P plus the rate at which P is changing with respect to this direction, multiplied by the extent through which we have moved in this direction. Okay, dou P dy multiplied by dy, and then this whole thing, so there's the pressure multiplied by this area, which will give us the force. Now, a word of not word of caution, but at least so that you guys are cautious about this. That is, here you see that we are just looking at the pressure forces. You might be wondering, what about viscous forces? Remember that viscous forces will create shear stresses. Okay, and which is something that may not be very intuitive. That on top of this pressure, viscosity will also create compressive stresses. Okay, so viscous forces, if viscous forces come into play here, you will have to put additional forces on this element. In this case, we are saying that we are looking at an inviscid problem. If you remember, we said that the flow may have viscosity, but for the viscosity to manifest, you need velocity gradients. If it is such that the velocity gradients are not anything major, then even with viscosity of a flow, the flow may not exhibit viscous nature. Okay, so the viscous traces can still be neglected, and what will come out of this kind of assumption is, if you remember, will be the Euler equations. So Euler equations are force momentum balance by ignoring the viscous forces or the forces due to viscosity. On the other hand, in situations where you cannot ignore the viscous forces, we will see that there is something called the stress tensor, and if you cannot ignore the viscous components, then it will result in a lot of these extra forces on each of these surfaces, which are known as the shear stresses. You will also see compressive stresses, and those will be because of the inclusion of the effects of viscosity. In this particular case, we are, our approach is to just introduce so our intent is to introduce the way in which the governing equations are being obtained. Okay, so of course, the more physics you include in these things, the the equations get a little bit more complicated looking, but nonetheless, it depends on the problem you are considering. For example, if you have say magneto-hydrodynamic forces, if you have body forces, then those have to be included. If you have shear forces, of course, those have to be included. In this particular case, we are ignoring body forces, we are ignoring the shear forces as well, and we are ignoring the compressive stresses as well. So this one is a simplified problem. Although it is simplified, doesn't mean that it is a not so useful assumption. So in regions of flow field, this is pretty much in some flow fields that is, for example, far away from the surface of a body, removed from the boundary layer, so it doesn't even have to be far away from the body. Your the gradients of velocity may be quite negligible, and you might still be able to use a inviscid formulation. So here you see that the force in the x direction, m times acceleration in the x direction. So m is rho times dx dy dz. So essentially, the mass of this parcel of fluid is nothing but the density times dx dy dz, the volume, and then now this mass will remain constant because we are looking at an infinitesimal parcel of fixed mass identity multiplied by the material derivative of the velocity. So essentially, we are measuring the velocity as we are moving with the parcel. Okay, and this whole acceleration results from, so the x direction, the x component of the force creates. So what is the x component of the force? So if you look at this particular arrangement of forces resulting from the pressure distribution, you get that the F in the X direction is this force. So P times this minus this force. Okay, so P times dy dz minus P plus dou P dou X times dx multiplied by the area. So the difference of these two is the net force in the X direction. So net force in the X direction is given by this. Once again, here this is the net force in the X direction for the simple case where we just consider the pressure forces or the forces due to the pressure distribution. There will be cases where you also have to take into account the viscous stresses, the compressive stresses, body forces coming from, say, various sources. It can be from gravity, it can be from magneto-hydrodynamic forces. There can be many kinds of body forces. For those specialized cases, you have to include terms arising from other sources of force into the Fx equation, Fy or Fz equation. But in this particular case, we are just focusing on the forces due to pressure distribution. Then we can say that rho times du dx and rho times the material derivative of velocity in the x direction is nothing but minus dp dx. So what we are saying is rho times this is equal to this, and then we are cancelling dx dy dz from both sides, and we are getting that rho times du dt, where d is the capital D or the material derivative, is nothing but the gradient of pressure in the x direction. Similarly, if you run the same thing in the y direction, you will get the y component of acceleration and force balance. Here you will get the z component of acceleration and force balance. Or rather, the z component of acceleration force balance will give you this result. If you combine them, you can write this form, which is rho times the material derivative of the velocity as a whole, velocity vector, is nothing but the negative gradient of P. Okay, where your this d by dt is given by dou by dou t plus u times dou by dou x, v times dou by dou y, w times dou by dou z, and you can also write it in this form. Okay, so here we saw a simple way in which the force momentum balance is considered, and we end up with the differential form of the momentum equation. So if you can see that essentially the rho times the material derivative of the velocity vector. So this is where you move with the parcel of fluid and you measure its velocity at time and location 1. You measure velocity at time and location 2. Of course, this change in time and location should be infinitesimal, and that can be related to the pressure gradient that is operating on that fluid element. This is again for the special case where we have only pressure forces that are being considered. If you have body forces, if you have viscous forces, then the expression for this momentum force will become a little different. So the acceleration term will still be the same, but the force term, so this term will have additional factors in it. Okay, so here we see that for inviscid assumption, we saw that the XYZ momentum equations look like this. If body forces are considered, then we have these additional terms of the components of body force in the three different directions. If viscous effects are included, your equation starts getting a little bit clumsy, and you see that we have these kind of terms that start showing up in our equation. So I'm just writing these three different terms, and we will see that these terms come from the inclusion of forces due to viscosity. Okay, so when we did not have viscosity, or rather when we were able to ignore the forces due to viscous stress, all these things dropped off, and we were able to get a much simpler form of the momentum equations given by these first three equations. But if you include, the forces that come into existence because of the viscous effects, the equations become a little bit more cumbersome. And each of these terms also can be expanded in terms of, we will see that from the rate of, the shear stress is proportional to the rate of strain. And we will see how these expressions are evaluated in the subsequent pages slides. So now we are going to look at what happens when we include the viscous forces, or the forces due to the inclusion of viscosity. In this case, now this is the component of force that is due to pressure we have already looked at. Okay, so we are looking at this surface and this surface. So on this surface we have P times dy dz, so dy, and this is dz, so P times dy dz. On this surface we have P plus dou P dou x times dx, as we have discussed in the previous slide, multiplied by the area. So this one is still from the pressure consideration that we talked about in the previous slide. Now you see that these special terms start showing up. And these are the viscous traces. So these are the shear stresses. So when you have the subscripts which are not the same, these are the shear stresses. On the other hand, when you have the subscripts being the same, these are the compressive stresses. Compressive or expansive stresses. Negative compressive is perhaps the expansive stress, but we call them compressive stress. So if you think of this one, so the two subscripts essentially signify, the first subscript signifies the plane of action of this shearing force. So you see that the first subscript is y. So this plane, so we're talking about this plane, so EFGH plane. So this plane is given, so this plane EFGH, so let me just use, we just highlight the boundary instead of putting the, okay, so if we think of the EFGH plane, this plane, the normal to that plane is in the y direction. So that is where this y comes from. So the first subscript on the, the stress term comes from the plane on which this stress is acting. If you look at this one, you see that here, so this one is acting on AB, AEFB. Just a second. Okay, so if you think of this shearing force acting on plane A, E, F, B, then you can see that the normal to this plane A, E, F, B is in the Z direction. So that is why this term comes into existence. So the first subscript tells you the plane on which it is acting. The second subscript tells you the direction in which it is acting. As you can see, the direction is in the X direction. Similarly here, the plane of action is EFGH, which is the Z plane, or sorry, the Y plane. So you see that the normal to this plane is in the Y direction, and the direction of the force is in the X direction. Okay, so for the shear stress, so if you think of this one, okay, so now this plane, the normal to this plane, AD, better to highlight the boundaries because otherwise some information inside this domain is kind of blurred. Okay, so if you think of this plane AEHD, this is an X plane, okay, because the normal to this plane ADHE is in the X direction. That gives the first subscript, and the second subscript comes from the direction of the force that we are considering. So actually in this particular page, we are trying to look at the contributors to forces in the X direction only. Okay, for example, you will have shear stress on this surface as well. Okay, that will contribute to the Z and the Y directions shear stresses. But in this particular visual or in this particular slide, we are just looking at the contributors to the X forces. Similarly, so we are, because if you can just obtain the X direction forces, from there you can obtain that rho times du dt is, so the acceleration of this parcel in the X direction is equal to the mass times the forces that are acting in the X direction. So here we are looking only at the contributors to the X direction forces. So here we have the forces due to the pressure imbalance between the left and the right surfaces. Here we are having the shear force in the X direction on the Y plane. Now this is something that I would urge all of you to look up, a book on fluid mechanics, and then to read up the portion on stress tensors, or just the shear stress. Although we introduce the term stress tensor, tensor essentially because here these stress terms have these subscripts, so you cannot just identify the direction in which they act. You also have to identify the plane on which they act as well. Okay, because you see that this is acting in the X direction, this is acting in the X direction as well, but the plane on which this is acting is different from the plane on which this is acting. So I would urge all of you to look up a book on basic fluid mechanics, where they have introduced the shear stresses. In fact, Anderson's book, chapter 15, where he talks about the forces on a viscous element, rather like on a element of fluid in a viscous uh, environment. There he introduces some of these things. Chapter 15 of Fundamentals of Aerodynamics. You can consult that book. So here at least we see that these shear forces, again, this is what we obtain from the Taylor series expansion. So the shear force on this wall plus the rate at which shear force is changing in this direction multiplied by the amount of the magnitude of that change in that direction multiplied by the top surface area. This is shear force on the bottom surface area multiplied by the surface area. So dx, and this is dz. So this product gives the surface area of EFGH. So similar to what we have done here, the rate at which P is changing with X multiplied by the amount in which we have moved through X to go from one face of the parcel to the other face of the parcel in the X direction. Here we see that we do the similar kind of thing. So here, for example, on this plane, you see we have tau zx dy dx. Dy dx again comes from this is dy, this is dx. So that's the area of this wall dcgh. And then when you move from this wall dcgh to the wall abfe, you move along the z direction. So that creates the rate of change of the shear stress along the z direction. And once you know the rate of change, you just multiply it by the extent of change, and you add what is here plus what is the change to get the new shear stress on this wall ABFE. So now we have the forces in the X direction. Now, what is this? What are these? So we are saying that these are shear forces. Shear is when you rub your hands against each other, each hand is um, trying to tug the other hand in its own direction, and that creates a shearing force between these two hands. Similarly, if you think about it, your this fluid element has velocities, but again, the adjoining layers have different velocities. So if let us look at this thing a little bit in detail. Suppose we are looking at this plane EFGH and the plane ABCD, and so the U velocity, V velocity, and W velocity. So U is the velocity in the X direction, V is the velocity in the Y direction, and W is the velocity in the Z direction. So if you assume the convention, so this is quite well described in Anderson's book on fundamentals of aerodynamics. So essentially, the convention is you think of U is increasing as you go with X, V is increasing in the Y direction, Z is increasing in the Z direction, and given this arrangement, it can be shown that your stresses will have this kind of direction. The shear stresses will have this kind of direction. So the velocities are increasing. So this is I should have had a slide on the distribution of these velocities. Okay, unfortunately, I do not have that distribution. So anyway, you read up this chapter from the fundamentals of aerodynamics, and in the next class, I will try to include some visuals that will help you to understand the direction of these. So again, these are compressive stresses. Okay, slightly different from the shear stresses. And here, since U is increasing with X, it can be shown that this wall has a pull on the left side. This wall has a pull on the right side. You can think of it as a spring that is being elongated, and the way it will pull its different sections. So nonetheless, this one is something that you can find in a textbook of fluid mechanics, and in particular in Fundamentals of Aerodynamics by Anderson. I will try to see if I can explain it better, but at this point, let us just take it at with the sense of that introduction to these things. Okay, so the goal is not to exactly derive these things because it needs a little bit more time, more discussion. I wanted to just give you a flavor of where these equations are coming from. So the best way to learn this is really to read from a textbook, because there is a little bit of nuance to these things then can be really explained on these pre-drawn forms that we are using in this semester. So here we have shown how these, so here this image is actually from Fundamentals of Aerodynamics by John Anderson, figure 15.11. See, this is that infinitesimally small moving fluid element. And on this one, I think just the X direction forces are given. Yeah. So here all the X direction forces are given. Okay, so if you think of, so here we have kind of broken these things into. So this is the composite picture of all the forces in the X direction. And if you take those into account, do the same kind of arrangement, that is, what we have done for the pressure forces. If you run the balance of forces, so once you have set up the shear and the compressive stress forces and the pressure forces on the x that are relevant to forces on the x direction, of course you have to do this for the y direction, do this for the z direction as well. Once you do it, for example, here we are doing it for the x direction, and then we are getting this form of the governing equation. Now you have some idea where this term is coming from, where this term is coming from, where this term is coming from. Now we will show that these terms again can be related to the rate of strain in the XYZ directions, but we will at this point not get into that part of the discussion. At least the kind of the ballpark approach of getting some of these equations. Now here, this is the energy equation, and as you can understand, what we are doing here is we are saying that just as in this case we run the mass conservation. Sorry, for this one, we are saying that the imbalance of inflow and outflow of mass causes a change in energy, within this region. Similarly, the inflow outflow of energy will also create a change in the energy of an element. So that is what is precisely considered here. So this one also is an infinitesimally small moving fluid element. Okay, so here we see that we have an infinitesimally small moving fluid element, and if you see, so here we are talking about the energy terms. Okay, so the energy, so this one is again a Lagrangian chunk, so it's moving through the flow field. These shear stress terms, we will spend a little bit of time in subsequent lectures, okay, on what these things really mean and what is the sign convention, how to obtain them. It needs a little bit of time to get into these things. We will touch upon them in a separate class. Here, at least, I want you to see that the work, which is so energy equation is essentially nothing but a work, energy, etc. balance, and you see terms like force due to pressure times the velocity, which essentially gives us a sense of see, work is force into displacement. Here we have force into velocity, which is essentially force into displacement per unit time. So essentially some work per unit time kind of thing is happening. Here also you see we are multiplying the shear stress with the velocity in that direction. Sorry, the compressive stress with the velocity in the direction of the compressive stress. This is also some work divided by time, because velocity is displacement by time. This one is volumetric heating. Okay, so heating, that is heat that is coming into this volume. Actually, this one is something to do with the heat that is being transferred to this volume because of. So if you see here, yeah, so this is something else. So this is the heat that is being conducted into the volume. Okay, so here we see some kind of a force, we see some kind of a work energy balance. So you have to figure out what is the energy that is given to this parcel, what is the work that is done on this parcel of fluid, and all this will lead to a change of the energy of this parcel. Okay, so if you see this multiplied by the material derivative of energy, so E is internal energy and V square by 2 is the kinetic energy. So substantial derivative of the sum of internal energy and kinetic energy can be related to this very large expression on the right hand side, which is nothing but, as I have discussed in a previous lecture again, the volumetric heating, the heat transfer through the walls due to temperature gradients, the pressure volume work, and the work due to the shear stresses and the compressive stresses. As you can now see, products of velocity and stresses are there, which is essentially the rate of work. Pressure and velocities are there, which is the pressure work. The conduction of heat through the surface of this parcel. So essentially by now we see a basic idea of how these equations are derived. We will continue with our discussion of these things and eventually get into the integral forms of the equations and the Reynolds transport theorem. And we will see that once we do the integral forms, a lot of important aerodynamic considerations can be solved using those integral forms. So we will talk about the integral forms in our next lecture, and we will see you in the next class. Thank you.